Hey guys, welcome back to another episode of Simuleos. Today is a very special day. I'm actually super excited for it. The stream's name is officially the Eigenstream because, you know, eigenstates, eigenvalues, eigenvectors, Eigenstream. No? Okay, that's fine. No, but today's going to be a fantastic day, I'm pretty sure. So here, let me go ahead and open up Zernal because I realized yesterday I did a very bad job of describing exactly what an eigenvalue is and exactly why it's useful for a number of different people. So, first things first, in the end, at the end of this diagonalization process, we're going to have a bunch of what are called eigenvalues. From those eigenvalues, we can get eigenvectors. From the eigenvectors, we see certain things with whatever, I guess, matrix we're working with that we would not see before. So I'm going to describe this kind of similar to how I did it yesterday. So let me go ahead and pull out my notebook and let me show you guys something that's very special about eigenvectors. By the way, I do have a notebook where I'm keeping all of my stuff nowadays, and it is completely filled with stuff to do on stream, so hopefully, well, when I say completely filled, it's like filled to page 10. I haven't done that much. But it is a kind of new notebook. I enjoy using it. It's pretty good. So I guess, as always, if you have any questions, comments, concerns, anything like that while I'm doing any of this kind of stuff, let me know, because I will do my best to answer any of the questions as they come up. And of course, I hope everyone's having a fantastic morning, because today is, at least it's Friday for me, which means it'll be Friday tomorrow for most of you guys, and that's pretty cool. You know, Friday, end of the week. I haven't decided whether I'm going to stream this weekend or not yet, so let me know what you guys think. If I should stream in the weekend, I might do that, might not. I haven't decided. If I do stream over the weekend, I think I actually want to do more Cairo stuff. Just take a few days off of the science, because, I don't know, I've been looking into the Cairo stuff on the side, you know, doing, what would it be? More or less the webcomic stuff again with Cairo. It was so cool. Like, there's so much stuff I could do that I just didn't know how to do. And so I thought, hey, if I'm going to do it anyway, which I'm probably going to do anyway this weekend, I might as well do it on stream. The other thing is, what is it? Oh, I also think I might do a video on actually just diagonalization, not even the DMRG stuff, just the diagonalization, because I think that might be pretty useful. Okay, so let me go ahead and pull some stuff out and get started. 1 second. There we go. Okay. So yesterday we did an example. Let me pull it out, where we basically showed the following matrix. Let's see. But I think it should be up to you if you'd like to stream or not. Just tweet or something. Yeah, maybe. So I guess maybe I'll have weekends optional. I used to do weekends all the time, and then I kind of stopped doing weekends. But I don't know. When I stopped doing weekends, I kind of felt like, I don't know, I felt like I was being lazy, and I hate being lazy. Okay, so we basically showed that this matrix right here had 3 eigenvalues. The eigenvalues are -3, -1, and 3, right? Now here's the thing. After finding these eigenvalues, we can create eigenvectors. If you remember, in creating the eigenvalues, we basically created a matrix like this. 1 minus lambda, 2, 0. 2, 1 minus lambda, 0. 0, 0, -3. Oh, minus lambda. And then what we did is we set the determinant of this guy equal to 0. And in doing so, we found that lambda could be equal to -3, 1, 3. By plugging these values back in as lambda, again, I'm going to draw this weird kind of plug sign, we found that we could have 3 potentially eigenvectors. The eigenvectors are as follows. So for -3, we have this equal to 1, 0, 0, 1. For -1, we have the vector, and I'm going to put a semicolon here. Let's see, what do we have? Of -1, 1, 0. And then finally for 3, we have the eigenvector of 1, 1, 0. I feel you. I guess if you don't have enormous amount of work to do, you might as well stream as part of your morning schedule. Yeah, but the thing is, I always have a lot of work to do, right? But I find that if I get up in the morning and I actually do work before doing actual work, I get more work done during the actual work day. Does that make sense? So like from 5 to 7, if I'm doing this stream, throughout the day I get a good bit of work done. If I don't do the stream from 5 to 7, I just kind of slack off in the morning. I get up around 6, which isn't that late, admittedly, but I get up at 6. I go work out around 7-ish. I don't stay for very long. Then I go to work, and I'm kind of not doing anything till 9:30, 10, and it's just like, I don't know why. I just can't motivate myself to work on days where I don't have a good start. And so that's kind of the thing. Anyway, so we have these 3 eigenvectors. Now, let's go back to the original matrix. Page, new page before. 1, 2, 0, 2, 1, 0, 0, 0, negative 3. And the eigenvectors, again, are the following. 0, 0, 1. Negative 1, 1, 0. And, of course, 1, 1, 0. Okay. So, let's do something special here. Let's multiply 1, 2, 0, 2, 1, 0. Hey, Lucky Box. 0, 0, negative 3 by the value 0, 0, 1. Okay? Now, obviously, you're going to get, let's see, 1, 2, nothing, 2, 1, nothing, 0, 0, negative 3. So we're going to get 0, 0, negative 3, which is going to be equal to negative 3 times 0, 0, 1. Okay? Now, I know everyone knows about eigenvectors and eigenvalues, but I just want to point out how cool this is. So we basically took our eigenvector, and it could have been any of these guys. I just took the first one. I'll take the second one in a second. And we found that when we do the multiplication, we basically get the same guy out as it was before. But in this case, we now have the same exact vector that we had before. So this guy right here is this guy right here, right? Okay, let me do this with another vector. Page, new page before. So again, it's 2, 1, 0. Oh, sorry, I already screwed up. It is 1, 2, 0, 2, 1, 0, 0, 0, negative 3, and let's multiply it by this one now. 1, 1, 0. Okay, in doing so, we do 1, 2, so we do 3, then we do 2, 1, 3, then the next one's 0, which is going to be equal to 3 times 1, 1, 0, right? That's pretty cool. Yeah, I totally agree. But I don't know. It's kind of, it just depends. So again, multiplying by an eigenvector gave us the same vector out with some sort of additional guy here, right? Okay, so let's try this one more time. Let's do it with just a random vector. So this is with an eigenvector. This is without an eigenvector. No eigenvector. Okay, so it's 1, 2, 0, 2, 1, 0, 0, 0, negative 3, and we're going to multiply it by any random vector. Guys, anyone have a preferred vector like 1, 2, 3, 4, 7, 9, 12, 0, 12? I don't know. If I don't get any suggestions, I'm just going to make one up. So, I don't know, 1, 0, 1. There we go. Random vector. I realized I could have made it complicated. I didn't want to make it complicated. Okay, so this means we have, basically, this is going to be equal to, let's see, 1, 2, 0. So this is going to be 1, 2, 1, 0, 2, 0, 0, negative 3. 681. We'll do 681 in just a second. And this is going to mean this is not representable. This matrix is not equal to this matrix. Any matrix is this way. Page, new page before. 1, 2, 0, 2, 1, 0, 0, 0, negative 3 times 6, 8, 1. We're going to get 1 times 6, 2 times 8. So that's going to be 1 times 6 is obviously 6. 2 times 18, so 22. 2, 6, 1, 8. So this is again going to be 22. And then negative 3. Not equal. Do it again. We have 1, 2, 0, 2, 1, 0, 0, 0, negative 3 times 1, 2, 3. And we're going to get 1, 2, 4. 1 second. Oh, I just realized this isn't 22. I'm a complete and total idiot. 2 times 6 is 12. This is going to be 20. Wow. Okay, anyway. So now we do 1, 2, 0. So it's going to be 1 times 2, 2 times 4. This is going to be 5. The next one is going to be 2 times 1, 1 times 2, which is going to give you 4. And the next one's going to be negative 3 times negative 3, which is going to be negative 9. Again, these vectors are not the same. Now, here's the thing. This is what's special about eigenvectors, and I realize it might not be so special now. Any other vector, when multiplied by your matrix, so we're going to do I lambda. Let's do it this way. I times some sort of vector is not going to be equal to some sort of constant, which I'm going to draw as C vector. But in the case of a eigenvector, I lambda is equal to some sort of constant times lambda. And that's incredibly cool, because this is what it means physically. If we've got a box, let's say, pretend I can draw in 3D, guys. Yeah, just can't draw in 3D. Okay, so let's say that A is some sort of rotation matrix, some sort of way in which we're rotating a box, right? That means that lambda is the axis in which we're rotating, right? So the idea is that by multiplying by this particular matrix or whatever, the lambda stays constant. The lambda is just stretched. It's not rotated or moved in any way, shape, or form. It is exactly what it was before, just with an additional scaling value. So in a way, you could think of the eigenvalues or eigenvectors as basically your x, y, and z axis if you're rotating along x, y, and z or something like that. In this way, we have very particular physical, values that the eigenvectors take. Now, we've done a lot of quantum mechanics on this channel, and some of you guys might even remember some of it, but maybe you guys didn't really fully understand everything. So, for example, a while ago we did a code that was called the quantum Monte Carlo code. In the quantum Monte Carlo code, we found the ground state. Okay? The ground state is an eigenstate. Here's how it kind of works. The state itself is this, oh gosh, that was horrible. The state itself was a weird Gaussian-like thing that we found. The vector, so this is the state. The vector is your ground state, and the energy was the energy that we had, or was the eigenvalue. So the energy is the eigenvalue. This is the eigenvalue. This is the eigenvector, and this is the eigenstate. And this is kind of how we're going to be looking at the quantum mechanical system that we're going to be going into in the future, right? The idea is that we have some sort of ground state that we're looking for, and to do that, we need the eigenvalues. And that's kind of an interesting point, right? Something that I didn't really highlight yesterday. The other thing is I did kind of a poor job of describing exactly what the Lanzau's algorithm is doing. So let me go back through and let me describe it one more time today, because actually yesterday, we and I should have been working. We're gonna get a quick sip of water. Yeah, so yesterday, when I should have been working, I did go through and look through more of the algorithm, and I realized it's a lot cooler than I gave it credit for. So let me go through and let me see if I can do a better job of describing exactly what everything is. And to do this, I'm going to basically put up a good bit of math jargon on screen. So forgive me, and if you have any questions, let me know, because I might not even be able to answer it myself, but I will do my best. Okay, so a few things that we need to talk about. One is something called a Krylov subspace. Now, I'm sure no one's ever heard of this before. I even asked a mathematician, and he'd never heard of this before. So don't worry about it if you haven't heard of this before. Basically, the idea is that we have three values to take into account. I'm going to draw a big K, and we're going to have A, which is some sort of matrix. Then we're going to have Q, which is some sort of vector. And finally, K, which is some sort of integer value. Okay, so it's 1, 2, 3, 4. Now, if we can create a subspace such that here, it's going to be Q. Then we have AQ. Then we have AKQ. A squared dot A to the K minus 1 Q. If we can create a subspace filled with these values, it means that our A value is what's called tri-diagonal. By this it means, let's say we have some sort of huge matrix like this. Only the middle and the two columns next to the middle are diagonalized. Or rather, you have basically a matrix that has three diagonals, right? Now, this doesn't really sound that impressive, but the thing is, in doing so, we can very easily go from tri-diagonal to diagonal. And if you remember, going to a diagonal matrix means that we have our eigenvalues. And the eigenvalues means that we can find our eigenvectors. And once we find our eigenvectors, we're set. So the idea then is that we have our tri-diagonal matrix and we do our diagonal thing. Now, what is the Lanczos algorithm doing? So the Lanczos algorithm, and again, forgive me if I'm mispronouncing this, does a couple of different things here. So the Lanczos algorithm is basically creating this Krylov subspace. By creating the Krylov subspace, it knows that the matrix has to be tri-diagonal. And then we can use some other diagonalization method after getting our tri-diagonal matrix, which you'll see today. But for the most part, the point of the Lanczos algorithm is it finds a good approximation of the highest and lowest eigenvalues. So we'll say high and low eigenvalues. And that's really cool. Because that means that we can find these guys pretty easily for an arbitrarily sized matrix, which is something that, we did like a 3x3 matrix and it took us like 20 minutes. Doing a 200 by 200 matrix is going to take forever, right? And that's kind of the idea. So here we can we can find the highest and lowest eigenvalues, which is incredibly useful. Sorry about that. There's one other thing I have to point out, and that is that there's something called a Rayleigh. What is it called? Rayleigh. See, whenever I say Rayleigh, I always think Rayleigh. I always think the Rayleigh range in light. But no, in this case, it is something else. It is, 1 second, I know I wrote it down somewhere. Here it is, Rayleigh quotient. Okay, and the Rayleigh quotient is going to be equal to, let's do quotient, is going to be equal to R, which is going to be equal to some sort of unit vector transpose A, the unit vector again, over U transpose U. And this is actually used a lot in our simulation so far. By high and low eigenvalues, I mean if you looked before, we had three different eigenvalues. Three, negative 3, and 1, I think. So high, low. That's all it means. It means that the tri-diagonal matrix, when we go back up, this value is high, this value is low, basically. In the diagonal matrix, once you do it. So you can kind of go from one to the other and find them pretty easily. That's the idea. And again, this just means your most, I suppose, dominant axes or something like that. I don't know exactly how to put that physically, but yeah. Okay, so after we do the diagonalization stuff today, we'll move on to the DMRG stuff maybe later today or tomorrow, depending on how far we get. With the DMRG stuff, I just want to point out that I have a guide that I will be following for the DMRG stuff because it's actually incredibly complicated. And the way I see it is I could spend hours and hours and hours toiling at my own version of the DMRG code, and that's perfectly fine. But the idea is that we need to understand what the DMRG algorithm is doing, not that we need to not that we need to code it ourselves. I mean, people have done this before. So I think it's perfectly fine to go through the guide, and I'll give you guys the guide as we're going through. Hopefully it will make sense. The guide is in Julia, so we'll probably switch to Julia when we do the DMRG, but for now we're using C++ for the Lanzas algorithm. Okay, that was a lot of information to get out, but again, we'll get to more of this information-dense style of talking once we get into the DMRG stuff. So for now, I think we're going to go ahead and move back to the code that we were working on yesterday, and go from there. I'm pretty excited to get started, I think. Pretty excited, I think. Okay, I'm going to move... how should I do this? I'm going to move this stuff over here real quick. I know you can't see anything, but I am moving stuff. I promise. Okay, so now how do I want to do this? I want to move back to this page. Good, okay. Anything else that I need to do here? No, I think that's fine. Okay, so let's pop this over here and pop that over there. And now let's cd into projects. That with Rogue. Projects, Simuleos. Over here, cd projects, Simuleos. And of course we need cd one more, DMRG. cd DMRG. Okay, so as of yesterday, let's go up here. I think if I run the last G++ command, you'll see that we have a whole bunch of warnings, but none of them are errors. The warnings are all coming from the eigen libraries. I don't exactly know how to fix all the warnings. Maybe we run it with, what am I running it with? Maybe if I do std equals C++ 11. No, that didn't help at all. I thought maybe. Okay, so let's go into the file we've got here. So the first one is going to be the Lanzas algorithm. Okay, so good. Let's see what we got. So we have this guy going through here. What I want to show is that we can return a tridiagonal matrix. So in the end right here, I'm returning R. But one thing I have not done yet is I have not created the Krylov subspace and go from there. Yeah, I'm gonna run for president. I think I'd be better than, well, you know, the other guy. Okay, so let's go here and let's see what we got. Or girl. I'm an equal opportunity runner. I don't know where I'm going with this. I'm sorry. Okay, so now what I need to do is create the Krylov subspace. So let me go ahead and go through here and make sure that everything's properly commented. So first, let me add a comment in here and say, I guess function for the Lanzas algorithm returns tridiagonal matrix. Can I find the X? Good. Okay, let's go up here and let's see what up here too. I'm gonna add the same comment here just to say I did. I'm gonna have to, oh, I misspelled matrix. Okay, I'm gonna have to go and let's see. I'm gonna have to create another function after this, but for now this is okay. So let's make sure this is commented. So creating random device seems fine to me. Double threshold. I guess I'm just gonna add a comment here, defining values. Defining, that's right. Okay, setting beta arbitrarily large for now. That's fine. Okay, generating the first R, 10 later. Yep, fix that. Matrix XD. Let's see. R Q A D. What does that spell? R quad. It's like far quad. Okay, so size t, I equals 0, I less than size. Yeah, that's fine. Who cares? So it generated the random r. And at this point, I think I'm going to see out r. Let's pretend I know what I'm doing. Good. Okay, so now we go through here, and this is the actual actual simulation. So right now we have just r I less than size. What I actually want to do is I less than 10. Now what I need to do down here, because in the end I'm going to have to return a value called t, I'm going to go here, and I'm going to say creating Krylov subspace. Okay, so what I need to do is I need to keep track of j, which I am. And let's go through here and create q. So we're going to say matrix xd q. And this is going to be of a particular size. And that size is going to be, let's see, r. Good. R is a vector. So we're going to say, let's see, rows first, then columns. So d matrix dot rows. And then j. So this means we have this many rows, or the same number of rows as everything else has, and then columns equal to the number of iterations that we have run. Okay, so now we're going to say, we're going to go through, and what we need to do actually, oh, actually, wait, this is, we need to keep track of our queues. What's the best way? You think we can, why don't we just, hey, chicken skill, you want to see something stupid? I'm going to do something real stupid here. Okay, let's go through and do this right. Where's q? Q equals r over beta. That's fine. Where do I define q up here? I'm going to remove the, well, no, I'm going to do, I'm going to do something stupid here. Okay, so I'm going to set vector of matrix xd q, and it's going to be d matrix dot rows. Oh, this isn't going to work. No, this isn't going to work at all. Wait, 1 second. Let me just comment out this. Let me go up, add vector. Okay, include. Let's do vector. Go down to the bottom. And let's comment this out for now. Oh, actually, I only have to comment one line. Did that work? Ah, no, it didn't. Oh, well, okay, maybe. Did that work? Oh. Let me return R. Oh, did I write that? 1 second, what am I doing? G++. See, the problem is with all these freaking error messages, or warning messages, I can't tell. Clear. Okay, let's try it one more time. Clara. Okay. I don't see anything red. It might have actually run. Ah, that's what I thought. Okay, so let's go up here, and let's change this up. So, Q of J, and let's put the J down at the bottom. J equals J plus 1. Q of J. R over beta, Q of J transpose, D matrix Q of J. Did I miss any? Oh, there's a couple down here. Q of J, beta times q of j. Okay, let's see what happens. Write this, go over here, g++. I think there was an error in there. Let me see. Maybe? No function matching call for std vector eigenmatrix. Ah, darn. I thought maybe. Okay, so how do we want to do this then? We need to create... See, the problem is this needs to be fast, right? And if it's not fast... Oh, it's fine. It's fine. It doesn't actually need to be that fast because we'll probably be using Eigen's negative diagonalization libraries from here on in. So this is just an idea to learn how it works, right? So let's throw that out the window. Let's just keep this as Q. Let's go down here. Remove all these QJs because that's me being, you know, just stupid. And then what I'm going to do is I'm going to define big Q up here. Okay. And then I'm going to remove these guys here. What I'm going to do is at the end of every one of these guys, I'm going to do q.pushback little q. Let me remove a.out. Let me see what happens if I do this. ls. Good. So this one didn't work either. Let me see. Identity is not a member of eigenxd. What is it saying? Didn't this work just a second ago? Let me go up here and let me comment this guy back out. I thought we had it running, but I think it's really hard to see running because we have all those error messages or warning messages. How do we ignore warnings? Let's go here. Let's do ignore warnings on G++. Let me see. There should be some sort of... Okay, let's do that. W. Okay, there we go. That's so much cleaner. I know there's nothing I can do about these warning messages, right? I mean, not that I can see. It's all from the eigen source. Oh, wait, 86? Let me see. Maybe there's something I can do. Let me see. Include ignoring attributes, template argument, internal. Let me see. Type def, conditional vectorize. Nah, nothing I can do, I think. Ignoring attributes on template argument. Okay, that's fine. So let's see. What do we have here? Eigen identity is not a member of eigen a matrix double. Let me see. So let me look this up then. Identity is not a member of eigen matrix XD. I know it's going to give me an error, but that's okay. I can add flags. Yep. Let me see. Creating a... Yeah, but the thing is, I think adding that... Here, I'll check in just a second. Identity matrix. Eigen C++. Okay, one second. Let's go here. And this is going to be the same page I was at yesterday. But let me see. Arbitrarily large. Where is it? I want to do identity. If I can spell it. There we are. So the identity matrix can be obtained by calling identity. Method is available for matrix, not for array. That's fine. Matrix double. I guess that's fine. We can do it this way. Oh, no, it's not quite fine. No, I need matrix XD identity. Wait, that's exactly what I have. Is it not? Oh, is it lowercase I? Is that the problem? Bah. Okay, let's go here, run this. And it runs just fine. Okay, so what you're saying is add ignored attributes. What did you mean? Ignored attributes. Apparently it's not recognized. That's okay. Okay, so let's go here. That one compiled just fine. Oh, let me keep that -W for now. And we'll remove it in a bit. Oh, this one. Capital W, ignored attributes. Yeah, so if I add that one in, capital W, ignored attributes, then it's gonna, oh, I don't know. It's okay. Not a big deal. Okay, so let's go here. And there we are. So we have everything working now. Let's go ahead and work with Q now. XX. Here we go, XX. We can probably delete these guys. Right here, go here, G++, enter. Okay, that one seems to work just fine. So let me go here and let me comment in what Q is. Q is the, maybe I should call it Krylov. Oh, fair enough. These are coming from W ignored attributes. I guess when you build eigen, it automatically does that. Let me see. Yeah, I think it's fine just to do W for now. Hey, hello. Oh, hey, Gusterman. Okay, so I'm going to change Q down here to, let me change it to Krylov. Krylov is the Krylovian. Is that how you spell it? Krylovian? Subspace. Oh. Okay. So go here and let's call it Krylov. Just so it's clear. Go here, where's the next big Q? Q. We're going to say Krylov. I don't really like how we have all of these guys, you know, like, I'm not a big fan of having single lettered named variables, so I'm going to change this to Rayleigh. And go down here, change the next one to Rayleigh. And again, it's probably Rayleigh. Sorry about that. Okay, is there any other R? There have to be other R's. Let me see. Rayleigh. Okay. And other R's. Am I missing an R? Let me see. R. Okay. I is that. I think that's it for the R's. Except down here. Oh. Okay. Write this. Go over here. G++. What? Okay. R is not declared in the scope. Let's see, 78. Fair enough. G++. I know I could have searched for them, just for the record. Okay, so next one, beta is fine. I'm going to call the A's alpha. Again, this is just a personal preference. You guys can do whatever you want with your code. That's perfectly fine. A is going to be alpha. Let's go and change the A down here to alpha. Okay, and what's next? Alpha down here. Okay. Let's see. Are there any other A's? Not sure. Let's go here. G++. Good. Now the last one is at Q. What is Q, actually? Q is going to be... I'm going to leave Q as is, little q as is. I can't think of a better name for Q. So let's go here and let's run it real quick. Let me see, a.out, user include eigensource, produce eigen. So there seems to be something stupid that I did. If you wanted a coefficient-wise or dot product perspective, well, that's great. I wish I... Okay. If it gave me a line number, this would be super useful. With derived eigenmatrix assertion a calls equals. Let me see. Did I mix up the columns and rows? Let me see. Initializing a matrix 4 3. So it's going to be 4 rows, 3 columns. It is rows first, then columns. Rows, columns, rows, columns. That seems fine to me. Okay, besides, the D matrix is square, so it doesn't really matter. Now what do we need to do next? We're reading in D matrix. Okay, let's see where this error is coming from. Okay, so up here we are outputting Q, which is fine. Oh man, I need to... Anyway, it's fine. Hey Cat626. Machine learning is fine. My roommate does a lot of machine learning. That's actually his research is related to identifying bees with machine learning. It's really cool. I don't do much machine learning. However, I would like to learn. It's something that I think nowadays in the research world that we're in, not knowing machine learning is actually kind of a hindrance to your advancement as a numerical scientist, someone who does code a good bit. Let's see, other good algorithms that you should learn that are somewhat related. Optimal control, for me, uses something like this. Yeah, I bet you're probably right, Gustorn. Okay, so again, machine learning is incredibly cool. I don't think it's like some sort of, like at this point, it's not going to create some sort of crazy AI that's going to take over the world. I'm pretty sure nothing like that's going to happen. Machine learning is good for what it is, and that's basically recognizing shapes and things like that, emulating how we learn, right? It's not quite the same as a lot of people give it credit for. Well, it's not even emulating how we learn. We give the computer some sort of, I guess, training set, and from the training set, it learns basically where things are supposed to be. But it is still pretty interesting, and it's something that we can look into in the future. In fact, there was a paper out not so long ago. Let me see. Archive. Machine learning authors, machine learning. Super Mario as a string. Yeah, this one. That I read and I thought it was pretty cool. I mean, obviously there was some information that I would like to have known beforehand, but it's basically automatically generating an entire Mario level with some sort of, I don't know if it's machine learning per se, but it's definitely using neural networks, and I thought that was pretty cool. In fact, I have the paper, and my friend and I are thinking about replicating that, so you might see some of that on stream. Okay, what am I doing? Matrix multiply in the loop. Let's go down here. What do we have here? Q.transpose times D matrix times Q. Okay, let me see what happens if I mess with this a little bit. So, what do we have here? We are outputting a couple of different things, but we're never outputting I. So that means it has to be in the loop. Okay, so Rayleigh divided by beta. Man, I wish this was a little bit better. No problem, Captain 626. Okay, so if you wanted coefficient-wise or dot product, use the respective explicit functions. Invalid matrix product. Assertion A left-hand side columns equals A right-hand side rows. Of which one? A dot transpose? Sunihito, hey, thanks for coming in. How are you? And yeah, I was gone for like a month and a half. I've been back for 3 days or something like that. By the way, guys, I'm still deciding whether to stream tomorrow or not. Tomorrow is officially Saturday for me, so I may stream, I may not. I don't know. I think it's probably a good idea to stream, but again, I haven't decided. Wutaka and I told me I should, so maybe I should. Okay, so Q.transpose, it's probably this one in the definition of alpha. D matrix, alpha times identity. Oh, actually, it could have been any of these multiplication symbols. D matrix, so what's the idea? Q.transpose is going to be a 1 by 12 matrix. The next one's going to be a 12 by 12 matrix, which should be fine. Then it's going to be 12 by 1 matrix. It's probably good. It's always a good idea for you to stream. Fair enough. I mean, tomorrow tomorrow it'll be Saturday, and if I do stream tomorrow, I might actually, and I know you guys maybe didn't like the Cairo stuff that we did, but I might do some of that again because I thought that was actually incredibly cool and could lead to some really, really good diagrams for some of my videos. Another thing is, if we can get this dang diagonalization thing to work, probably tomorrow during during the day, I'll make another video. Hey, I care. Thanks for coming in. Doing great. Probably passed my final sysadmin project. Fantastic. Also landed a kind of IT job. Doubly fantastic, which means you are way ahead of everyone else in getting a real life. Well, ahead of me anyway. Okay, so what do we have here? Let's go through and figure out what the problem is. I could use some sort of debugger, but debuggers are for chumps. Let's go through here. And let's just define a couple things. So what does this mean? Alpha has to be a double value. What? Alpha should be a double value, shouldn't it? Let me think. So if we have 1 times 12, times 12 times 12 times 12 times 1, it's going to end up being a 1 by 1 matrix, isn't it? What is alpha? Why did I define alpha as a... Alpha should just be a double. Let me see here. A is equal to Q transpose times A times Q. Yeah, should it be a double? Did I... Wait. Am I doing something stupid here? Let me do this analytically real quick. New page before. Okay. Okay. If we have a 1 by 2 matrix multiplying a 2 by 2 matrix multiplying a 2 by 1 matrix, let's see, this is going to be 1, 2 times 1, 0, 0, 1 times 1, 2. Okay? This is going to mean these first two are going to give us a matrix that looks like this, right? 1, 2. So let's see. 1 times 2, 2 times 0. It's going to be the first element. 1 times, yep. So that's going to be that. And it's going to be multiplied by 1, 2. So it's 1 by 2, 2 by 1, which should be fair. And then 1, 2 plus 2, 1. So this is going to give us a 1 by 1 matrix. What was I doing before? Let's go up here. Yeah, I'm pretty sure I just defined alpha as something stupid. Let me see. What do we have here? I'm pretty sure alpha is supposed to be 1 by 1. Anyway, let's see what happens. I agree, Gustern. We'll do that. So let's do std cout beta and line. Std cout q and line. Std cout alpha and line. And I think that's where it's gonna break. So let's quit that. Go over here. 1 second. G++. A.out. Okay, so what do we have here? And let's also do something else. Let's do I don't know, beta is n. N. Okay, there we are. And we're gonna do q is there we go. And then we're gonna say alpha is. Aw, man. 1 second, gotta go up here. Mismatch of these guys. Okay, let's write this. Go down here. G++. A.out. Okay, so we have beta is one single value. Is that right? Rayleigh norm should be. Q is a 1 by 2 matrix, which is going to be 0.3. Probably fine. Alpha is a 1 value. That's fine. Okay, let's go to the next one then. Rayleigh. So std cout Rayleigh is then Rayleigh n G++ A.out. Okay, so it breaks on the next one. So first of all, I guess it doesn't matter. We'll see what happens with alpha. Okay, so Rayleigh is this. So it breaks on this one. D matrix alpha times identity times q minus beta times q. So let's also print out the identity here. So we're going to do... Oh, that's probably it. It's probably the alpha times identity. Yeah, I bet you that's probably it. Because that's going to be a 1 by 1 matrix times a 2 by 2 matrix, which doesn't make any sense. So let's go up here. And let's define alpha as a double. So I guess what I can do is comment this guy out here. Go here, add in that. And then define... Yeah, alpha should be a double. D matrix times Q. Alpha cannot convert constant type general product. Oh, maybe I need... Let's try this. Okay, dot Q. And then let's just say alpha of 1 or 0. Oh. 1 second, gotta go up here. And let's try this. And seem to compile, A dot out. There we go, works just fine. Okay, so the problem there was that alpha was defined as a 2 by 2 matrix, but it only had one value in it. And that value was, how do I put this? That value was in the 0, 0 element. So that's fine. Okay, so let's go through and let's see what we have. So we printed out identity. Oh, no, we didn't. What? Alpha is... No, I never printed out the identity matrix. I is 9, but we go up to 10. That's fine. Okay, so now what should we do with alpha? Alpha should still be a 1 by 1 matrix. Which I guess is fine. Now, what was the problem before when we tried to define it as a double? I don't remember. Alpha. Let's try that one more time. G++. Okay, alpha cannot be used, and that's fine. Error, cannot convert constant type general product. Let me see. To eigenmatrix, to double. It's fine to leave it as a 1 by 1 matrix for now. No problem. We can go back and fix it later. Oh, man. I just want to kind of get this done because, again, as I mentioned kind of earlier, this is kind of just an example of how the Lanczos algorithm works. It doesn't necessarily matter that it's the most efficient code. So what I'm going to do is... I guess it's going to be Rayleigh vector or something like that. And let me see. Now I need to say alpha is actually just a double. Sorry about that. What? Yeah. Yeah, you're totally right, Gustron. A dot out. There we go. Just fine. Now I could do a number of things here. Yeah, that's what I just did. It's a 1 by 1 matrix now. Okay. So, what's next? Well, let's go down here. And now, right now, we're returning Rayleigh, but we also have the Krylov subspace. What I want to do is... I can probably get rid of these C-outs. Or at least comment them out. So let's do that. Okay, so they're commented out for now. And let's go here, and let's do what we need to do. So we already have the Rayleigh, or not the Rayleigh, the Krylov subspace being created. So now what we need to do is create what should be the identity matrix. So here in the notes that I have, they call it IEYE, which I guess is fine. What I'm going to call it is something else, matrix XD. And this is going to be called, I'm just going to call it ID, wait, let's do Krylov ID. And it's going to be equal to, should just be Q transpose times Q. So this is going to be Krylov. Let's see. Oh, now that's interesting. Okay, because of the way I created the Krylov subspace, again, just as a vector of, well, essentially vectors. Now, the thing is, if I go to a standard value, right? This should be Q transpose times Q, right? So we're looking for Krylov transpose dot transpose times Q, or Krylov. But the problem with that is that I am kind of an idiot here, and I didn't think about... So Krylov has to be a dynamic matrix, right? Because in here, I don't know what value this is going to go up to. Here we've kind of set it to 10, but it could be anything. So for now, what I'm probably going to do, just so that this goes a little bit smoother, is I'm going to set it to an arbitrarily sized value. So we'll say matrix XD Krylov, and this is going to be of the appropriate size, which is going to be D matrix dot rows, and then 10, which is the number of iterations we're going to. Down here, instead of doing Krylov push back, I'm going to say this. Krylov of I could do a for loop here and assign all of them appropriately. Maybe that's the way I have to do it. Unless there's a way to take just a particular column. Oh, sorry about the yawn, guys. Unless there's a way to take a particular column and set that as another guy. Here, let me just do it this way. So we're going to do for size t I equals 0, I less than d matrix dot rows I plus plus. Oh, I've been trying to do plus plus I. Okay. We go here, and now we just do everything we need to do. So we're going to say, 1 second. What is it? We're going to say that Rayleigh of I is first, J is second, is going to be equal to Q of I. Okay, that one seems to compile just fine. Then we go down here and we say Krylov identity is going to be equal Krylov transpose times Krylov, and then we just print out, so std cout. Oh, wrong way. Krylov identity. Now, the identity matrix doesn't really matter. We're not going to use it. It's just kind of a check. The thing we actually care about is T. And T is going to be equal to Q transpose times A times Q again. So this is going to be Krylov transpose. So we're going to do matrix. Did I already define T? No, I don't think I did. XT. T. And what is the size of T going to be? It should be... Yusuf Basri, hey, thanks for coming in. Not much, just kind of working on the code still. How are you? So T is going to be Q... Pro Infinito, hey, thanks for coming back. Let me see. Q prime A Q. Okay, so what does that mean? What is T going to be in the end? It should be... Wait. Q transpose is going to be how big? Wait. This is... Q itself is d matrix rows by 10. So Q transpose is going to be 10 times d matrix rows. So in the end, does that mean we have a 10 by 10 matrix? What? That doesn't make any sense. Let me see. Check diagonalization at the end. Identity, that's fine. Yeah. No. What? It is originally a d matrix dot rows. Okay. So the transpose is going to be 10 times d matrix dot rows, d matrix rows, d matrix rows. Yeah, this looks like it's a 10 by 10 matrix. Let me just print out the matrix that we have. And then let's go from there. So it's going to be equal to Krylov dot transpose times d matrix dot, oh no, it's just d matrix times Krylov. Okay, and then we should be returning t, and let's see what happens. So we're printing out Krylov ID, and what do we need to do here? We need to say end line, but before this I also want to say the identity matrix from the Krylov subspace is, wait 1 second, n. Let's bring this down to the bottom. Okay, let's see what happens if we run g++. Yeah, okay, there's something that I did stupid here. Let's see, Krylov ID, oh, that would be it. Oh, also that. Why do I keep pressing O? Okay, there we have that. Error, expected primary expression before t. That's probably fair enough. Okay, let's see what happens if we run it now. Expected before equal sign. Matrix t. Okay, that's fair enough. Let's go here, add in a semicolon, go down here and say t is equal to that. G++. Okay, a dot out. Something broke, fantastic. Okay, but we know it broke after this point. So, it's probably this one. Let me see. Let me see out something. SVD. See out. 1 second, guys. The Krylov transpose is n. Let's do Krylov dot transpose and n line. Over here. Oh, sorry. G++. A dot out. Oh, interesting. Okay, so it doesn't like, just as a sanity check, let me also std something here. Finished loop. Why am I not able to type today? G++. A dot out. Okay, so it doesn't, what? Oh, it must be in here then. CD, C out, I, end line. Ha. Okay, that's fair enough. Okay, so let's go here. It's going to be I, J, I, 0. What? Relay of IJ, Q of I, 0. Should be fine. Oh, wait a minute. Maybe it's because this J is equal to J plus 1 has to go to the bottom. Nope, that didn't help at all. Did it get to 1? Maybe. Okay, let's go up here and let me see what do we have. It's going to be matrix Rayleigh. Oh, that would be why. This has to be Krylov. Okay. That one seemed to run just fine. What is it that just happened? Wait a minute. The identity matrix from the Krylov subspace is the following. It has 1s in the diagonal. That's fine. But I don't think this is right, because it also has ones down here. Dang. Okay, let's see if we run it for longer. Okay, so let's go instead from 10. How big is this matrix? It's way bigger than I was expecting it to be. No, that's a 10 by 10 matrix. That's exactly what it's supposed to be. Okay, so in the Krylov subspace then, we have a 10 by 2 matrix. Okay. So, we create Q, and then we say Q transpose AQ. That should be what it is in the end, I think. Oh, man. Well, guys, remember how I said at the very start of this episode, if you were here, that I wanted to maybe get into DMRG at the end of today? As always, my estimates are incredibly and totally wrong. We're probably not going to get into DMRG at the end of today. Today's probably just going to be diagonalization day, which is apt because the name of the game is the Eigenstream, so that's fine. Why did I go here? Oh, I know why. I wanted to look up the Lanzo's algorithm, because there's actually a page on this on Wikipedia, which isn't the best page, but I figured if you guys are interested, this is the algorithm we're working with. And I know that down here, when I read through it, yeah, so in the end, there's another one also. One second. This one? Yeah, this one. Okay. So this is an example algorithm that we can work with. So I will go ahead and post this too in chat. Okay. So we scroll in, move over a little bit. Okay. So this is basically what we've got. Q transpose Q. This is actually the exact code I'm working with. I just wrote it down on my notebook. Well, kind of. I have a little bit of a different, but it's pretty much the same. Okay, create a random symmetric matrix. D. Okay, that's fine. We did that. Iteration with j equals 0. Fine. Did this. Check orthogonality. Fine. Let me see. What did they get out at the end? They get out a pretty good identity matrix and a pretty good tridiagonal matrix. That's fine. But it was with D equals 200. And in the end, the tridiagonal matrix is a 3 by 3 matrix. So let's try this again. Let's try this with a much, much larger matrix to work with. How did they get a 3 by 3? Oh, it's because J only equals 3. Good, okay. So we'll do J equals 10, or you know what I'm saying. We will have this guy go up to 10 like we did before, except in this case what we're going to do is we're going to read in a much larger matrix. So before we had matrix XD 2 by 2, let's go through here and let's do matrix. We're going to set this equal to some arbitrary value. So we're going to say size. Do I already have size defined? I probably do. And size is going to be equal to 200, 100, 200, whatever. And let's see, do I have size defined? Here it is there. Size T, size T, size. I have defined in here. Oh, as the exact same value. That's fine. Okay, so we're going to do here. And we're going to say size. Size. Oh, I can't type. Okay, there we go. Size and size. That's fine. Let's go here. And let's actually just go through and initialize a random matrix. So, 4. This is fine. Size T. Oh my gosh. Equals 0. I is less than... oh, wait a minute. What am I reading in? Wait. When I go to yeah, okay, it is A that I'm reading in. That's fine. So let's call this the same thing as I'm calling everything else. Let's call this D matrix, just so I don't get confused. And then we're going to do D matrix dot rows. And the thing is, we have to make this symmetric, so we're going to do plus plus I here. And now what we're going to do is something a little bit different. We're going to say that D matrix of... Wait a minute. Oh, yeah, we need the random device. Anyway, we're going to say the D matrix of... oops. For size T. I'm sorry, this is a little bit confusing. Equals 0. J is less than I. Then we do plus plus J. Go here. Add some spaces. Not an A. And then we go here. Okay. We're getting there. Okay, so D matrix of IJ is going to be equal to some sort of random number pulled from some sort of place, right? So what I need to do, and then after that we're going to set D matrix of Ji equal to D matrix of Ij. There we go. So now we just have to pull the random. So the first thing I need to do here is setting up, set up device. And what I might do, this is fine. This is fine. I'm just gonna, for now, keep these guys the same. And then later on, we'll deal with the repercussions. So we're doing the same thing here. And then here, all we need to do, I think, is just call the random device. So let's go down here and make sure. 1 second, beta. Where did I use random? I think I used dist. Yeah, dist gen. Good. And where are we? We are right here. Dist gen. Okay, let's go down here and let's output more values. Matrix. I don't want to output that many values. Let's just output one column. I0. Oh, let's pull something in the middle. 100. There we go. Okay, so we have that. std cout a.rows should be fine. I will output matrix D. Rows. And then here we say matrix D. Good. Q seems fine. Oh, I don't need to generate this identity matrix anymore. We're pretty sure it works. For size T, IQ is equal to q.rows. Also probably fine. Okay, let's go here, write this. Oh, sorry guys. Go here, do G++. What did I do? Matrix D was not declared in the scope. Oh, because I called it D matrix. So let's go through and let's fix that then. Matrix D with D matrix G. Oh, what? S matrix D matrix. There we go. A was not declared in the scope. C out. Where's C out? Here it is. Matrix. Matrix. Okay, good. Done is done. Write this. Go over here. G++, and let's see what happens if we run a.out. Okay. What is it that I'm looking at? Okay, so first of all, what is this up here? Oh, it's a Krylov transpose. Okay, that's fair enough. We probably don't need that out anymore. So let's go ahead and dd. The identity matrix from the Krylov subspace is Krylov ID. That's the one I'm interested in. Where is it? Oh, I bet this is what it's supposed to be. Yeah. Okay, again, we do get ones along the diagonal, but that's not exactly what I was hoping to get. And then for some reason, Though I'm not quite sure why. We're not outputting... Oh, well, that would be obvious. Why not? Okay, so we have Q for size T. For size T, J equals 0. J is less than Q dot calls plus J. And we're going to output IJ. Maybe we should do this a little bit differently. Let me see. We should probably do it this way. QIJ. And then after that we do... so we put out IJ, 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 J. And then we do STD. Cout. Oops, sorry about that. New line. Oh. G++. A dot out. Oh, and we should probably put a tab. That way we actually can see what we're doing. Let's do G++. A dot out. Still doesn't help that much, so what I'm going to do is I'm going to go down here and change this from 10 to 3. So let's go up here and say, I don't know, int j equals 0, j tote. And now let's go through for each of the 10s. 10 here, 10 there, and we're going to call it j tote. Next, j tote. Next, j tote. J tote. Okay, 100. Nope, that's not what I want. I want j tote. There we go. I'm gonna set this equal to 3. Now we're gonna do G++. A dot out. Okay, so that's not an identity matrix. Pretty sure. What did we do wrong? Well, let's go through here and let's see if we're doing the Rayleigh matrix thing right. So it looks like it should be D matrix minus alpha is what they call it, times the identity matrix, times Q, okay, minus beta times Q. Okay, that looks identical to what we have. But let me go back and check. So again, the link that I sent last, this qubitulm.com, it's University of Ulm, I think, in Germany, I think. Anyway, that particular lecture right there goes through with a bit of a different algorithm. So let me make sure that the algorithm that we have here matches the algorithm that they put there, except they have standard iterations. They have J0, J1, J2. Here we're going through everything in a different way. So let's see if they match up. So first of all, for the very first iteration, they say that R0 is going to be equal to some sort of random vector that is of D size and one length. So it is just a random vector. Here we have here, and we did output a random vector. And let's not output J anymore. What are we outputting? I? We don't need this finished loop. Where's our cout that's actually couting anything? Wait, where is the cout? 1 second. Cout. That's fine. Fine. There it is. G++. A dot out. What is this outputting? The identity matrix. Oh, that's just one column. Let's see, 1.55911. Should be okay. Okay, so let's go up to the top and let's remove that too. D matrix here, or comment it out. Wait, what? What's I doing there? D matrix. Oh, this is... Ah, it's fine. We'll comment it out. It's not necessary. Over here, G++. A dot out. Okay, it's still outputting. I thought it wouldn't output. It must be... What do we see outing? Is that down there? 1 second. Let's go here. Oh, wrong way. G++. A dot out. Okay, 1 second. What is this actually outputting? I don't understand what this is. So this is the very first thing that's being output. Where's our first C out? There. Those aren't counted. That's counted. That's counted. Rayleigh. Oh. Guess that's fair enough. Okay, so let's go here. G++. A dot out. Okay, good. This is what I wanted. So first of all, again, the identity matrix kind of looks okay, but it's not anywhere near where we want it to be. And the this is not tridiagonal. Okay. Now we can check the iterations with what they have in the Ohm in the Ohm lecture. Okay. So the first one, they say R naught is equal to a random number, which is fair enough. And then they say beta is equal to the norm of that random vector. That's fine. They say Q is equal to the random vector divided by beta. Also fine. A is equal to Q transpose times D matrix times Q. That is exactly what we have. Q transpose D matrix times Q. Okay. Then they say, hey Edge226, what's up? I guess it goes okay. Now what's the next one? So it says Q transpose A. That should be fine. Now I calculate the Rayleigh number again. But this is for them, the next iteration. So they calculate J again. Okay. So now they do J. Wait, R. 1 second. Sorry about that. Then they calculate another B, another Q, another A. So they calculate R, B, Q, and A every term. We have B, Q, A, and R being generated every term, and then we're pushing back the Krylov subspace. So that should be okay, right? It looks like we're doing everything in the right order. Now, what do they set R equal to? R, for the very first time, is just A times Q minus A times Q. This is little a times Q. Big A times Q. 1 second, let me think. Does that make sense? Yeah, it probably makes sense. So A is going to be some sort of single valued number. Okay. The next one is A times Q minus A times Q minus B times Q. Okay, interesting. So they never do this formula that we're doing here. We do it a little bit differently than they do. Let me just see what happens if we do something a little bit special here. So what I'm going to do is I'm going to comment this guy out. And again, I'm following this guy right here. Copy. Paste. Or just this. Nope, nope, oops. Oops. Sorry. Oh man. Sorry. There we go. Got it. Okay. I thought I had it copied, but apparently I didn't. And this is what I wanted. There we go. Got that one done. We're following this guy. The algorithm is on page... let me see. I don't even know what page that is. It's somewhere near the middle. And there's a MATLAB code that we're looking at. Okay. So, what I want to do is I want to follow what they have exactly and try to match it up with what we have. So what is beta for the first iteration? Beta is going to be the normal of the Rayleigh number, right? Okay, that seems fine to me. And let's just go through here. Since we only have 3 iterations, let's just force those 3 iterations to be who we want them to be. So, maybe I can do it this way. Switch. Should I do a switch here or if else? I guess it doesn't matter. Switch I. Case 0. Really, it's going to be equal to. Looks like it is just Q transpose A Q and Q. So it's going to be Q dot transpose times the T matrix times Q. Case 1. And in this case, Rayleigh is going to be equal to. Oh, actually, wait a minute. It's just case 1 and case 2 for them. So then R is going to be equal to D matrix. If I can spell. Let's see, D matrix times. Oh, they mix up the Q's, don't they? Interesting. Okay, so we're going to do D matrix times. It's going to be Q2. So this should be the current Q. Yeah, it's the current Q. So we're going to do Q minus A, which is our alpha, times Q. Then we're going to subtract out beta times 1 minus Q. So we're going to do Krylov. And we want to pull a whole column. Let me think. I guess... Is it this? 1. Let's see what happens. Does that even work? Yeah, okay. How to pull a full column in Eigen. Eigen. I want using a column of a matrix eigen. C++. Block operations, columns and rows. 1 second, I have to get a quick sip of water. Access the column as a matrix. Okay, there we go. And this actually makes our lives a little bit easier. So let's go down here and let's do that. Krylov call of 1. And then when we go down here, we start pushing things back. Let's change this up a little bit. So we're just going to say Krylov dd of call of 1, or rather dot call of j is going to be equal to q of wait, it should be equal to q. Yeah, and that should be okay. So this means the first column is going to be q 1, I guess, and the second column is going to be q2. So what we want to do up here when we call Krylov column is we want to do of 0, I believe. Okay, let's see what happens if we run this. I have a feeling it's not going to work. Maybe it will. Yeah, totally broke. Okay, good. Let's see out some things. I'm pretty sure we get down to this part right here. Just to make sure, let's go here and let's do G++. Yes, we get to alpha, no problem. In fact, apparently we go through 2 iterations, which is different than what I was expecting to happen. Okay, so let's go here and let's see the identity matrix. maybe we go here, and at the end here we std c out j, end line. Then we do g++, a dot out. We got to 1, and we did not get to 2. Okay, so the problem is in 2. So it's going to be d matrix times q. Q is going to be a some sort of like, I don't know, 200 by 1 matrix. D matrix is 200 by 200. So this is going to create a 200 by 1 matrix minus alpha. Let's try alpha of 0, 0. G++, a dot out. There we go. That one worked just fine. Okay. This is still not giving us what we expected to get. So we're still doing something wrong then. Q3. Rayleigh. Okay, so we're going up to 3, right? So we do 0, 1, and 2. Okay, in the 0th iteration, Rayleigh should be just a random number. Hey, Implete. It's been a while. Yeah, I was gone for like a month, and now I'm back for, well, I should be back for good. But yeah, I should be back for good, I think. But it kind of depends. So again, obviously I travel or something like that. I'll be gone for a month or whatever it happens to be when I travel. My advisor actually wants me to go to somewhere at some time. I don't know exactly where or when. He said either Australia or somewhere in mainland Japan. I don't know. So at some point I have an additional travel planned, but I have no idea when. So we'll see how that goes. Okay. So it's going to be Rayleigh over beta. And I just realized something. This should be case 0. And this should be case 1. And then for case... Yeah. Okay, this should be right. Right, this, go over here. G++. A dot out. Okay, what do we have here? This looks about right. Fantastic. Okay, so what do we have? I realize it's kind of hard to see over here, but we have 1, 1, 1 along the diagonals, and everything else here is times 10 to the negative 15th, pretty much 0. And then we have a tri-diagonal matrix in here, where the edges over here are, you know, basically 0. So we have our tri-diagonal matrix. We have our identity matrix being generated from our Krylov subspace. Everything seems fine. The problem is, this is not, we can't do this for a larger matrix, right? So we have to, we can only create basically 3 eigenvalues. Kind of, in a way. So we can only create a tri-diagonal matrix. I've heard of this new thing on Twitch again. Levenshtein distance. I don't know what that is. And also that's a very good motto to learn every day. What is this? In information theory computer is the string metric form for measuring the difference between 2 sequences. Informally, the Levenshtein distance between 2 words is the minimum. Oh, actually, I do know what this is. It might be another distance that I'm thinking of, but this is used a lot for biology and stuff like that. When I took my biology course here at OIST, we did a lot of numerics and stuff like that. And one of the things we did was calculate the distance between 2 strings. Super cool. Lots of fun. Okay, so now what we have to do is make this in a way that is iteratable. Iterable? Is that a word? Iterable? You're using it. It's fine. Rayleigh is equal to D matrix minus alpha. Oops. Screwed something up here. So again, the guide that I'm looking at says that the Rayleigh value should be the big matrix minus alpha of 0, 0. Oh, I bet you that's it. Okay, let's try this again. Let's comment out the switch. And let's go down here and do this. Up here, we're going to say it's not Q, actually. Now another thing is usable in biology. Learn every day. Yeah, so biology is super interesting. Not computational biology. What is it called? There's a particular word for doing numerics, and by numerics I mean work on your computer in order to find a result. There's a particular word for it. No room for degradation anymore? Let me think. What is it? It's shoot, I'll call it computational biology for now. I don't actually remember what it's called, but it's incredibly cool. Certainly something to look into. Beta times Q, and this Q actually has to be from the previous Q. So what I'm going to do is it's going to be beta times Krylov of call of J minus 1. And now, because I am... I'm sorry, guys. Let's go here. There we go. That looks bad. Okay. D matrix minus alpha times identity times Q. Krylov call minus 1. Fun fact that I have your stream in bookmarks but never followed you. Oh, that's fine. Appreciate it, Implete. Okay. Rayleigh D matrix. I think this is right, right? What could possibly go wrong? Let's check though real quick. So before we're using Krylov column of 0, and this was for iteration 2. I think I got something wrong here. Let me run this and let's see if it works. And then we'll check. What? Oh, I misspelled Krylov. Krylov. Okay, let's go over here. G++. A dot out. Broke. Yeah. Maybe that's true. Edge 226. It's just it has the word biology in it. Lensons stuff, as I know, using for video rendering or something, it's used for a lot of things. In particular, it's used it's used for anything that you need to diagonalize matrices for. So if you need to find the eigenvalues for something, the Lensons algorithm is used to find those eigenvalues. And when it comes to images and processing images and videos and stuff like that, eigenvalues are incredibly important for finding basically... I'm not actually very familiar with this. I've got a friend who does this all the time, but it's very useful for... I think colors and things like that in images. But again, forgive me if I'm wrong there. I could very well be wrong. Okay. And this is because j is equal to 0 at the start. I see. Okay, so let's go up here. And let's do if j is greater than 0. Oop. We do this. And let me just fix this up. Oh, really? I didn't know that about the OBS stuff. I mean, I use OBS, but that's just because it's an easy guide to use for Linux. Let me see. I imagine that's what most people use, though. OBS for streaming. And then we're going to say else. Can I spell else? Probably not. Okay. And go here. Copy these guys. I just realized I made a stupid up here. See, then I said a stupid. What does that mean? I made a stupid mistake. Okay. Minus beta. Oh, nope. It should just be times Q. G++. A dot out. Oh, it still broke. Dang it. Okay, so let's get this working. And then we'll check to make sure it's actually working correctly. So if j is greater than 0, we go through here. Let me output some stuff. Because I don't like this right now. So let's see if we get through this if statement. So we're going to see out j. We do not. So this if statement right now is posing a problem. So let me see out here. std cout 1. This is just to check to see where we're at, so it doesn't matter what we call it. std cout not 1. end line. G++. A dot out. Okay, we got to, what? If j is greater than 0, j should be equal to 0. Can you say some sort of books or how to practice with math better? Okay. Mathematics for me does not come intuitively. I'm just going to be honest here. It's not something that I can do right off the bat. Now, I've got friends who can they can do math. You know, they are good at math. Me, no, I'm mediocre with math. That said, if you want to learn it, for me, it's always best to apply it to a physical system. So the books that I learned math the best with, if you give me just a second. Here, let me pull out a book real quick. It's kind of in the background. Give me 2 seconds. Actually, the book I was looking for wasn't even there. But the book I was thinking about was Griffith's Electrodynamics. At the very first chapter of that book, it goes through all of the necessary math you need for, what would it be? All the math you need for vector calculus and stuff like that, which is all you basically need for physics. Linear algebra and stuff like that is pretty much covered with your basic quantum mechanics books. And I guess also with, for differential equation solving and stuff like that, also in quantum mechanics. Basically, I learned all of my math from physics. Now, I took basic physics classes, but that doesn't really help that much. So unfortunately, that's my only advice I can really give you. Maybe learn a system, or find a problem you want to solve, and then learn the math to solve that problem. So for example, if you wanted to learn something more about matrices, you could learn about, I don't know, some sort of problem that requires matrices to solve. For example, this one requires a good bit of matrix algebra. So if you need to learn more about something, I guess I always just find a problem to solve that requires that, so I have to move through it, you know? Because learning math in and of itself is really difficult for me, but learning applications of math is usually pretty easy. So that's, I guess, my only advice. I'm sorry if it doesn't really help that much. Okay. For some reason, we are immediately at a stage where j is greater than 1. Alpha is this. Do I not? I see out j. Okay, let me see. Where do I define j to begin with? I thought I defined it up here. J equals 0. J tot is equal to 3. Do I redefine j? No, it doesn't look like I do. What the heck? If j is greater than 0, C out. Oh. D++. A dot out. There we go. And it looks like it is correct. Fantastic. Okay, so this should be iterable. Iteratable. DD. Let's leave this in for now because I want to try something. I want to increase j tot to 10 to make this a little bit more obvious. To 10. And then I want to do something special. What I want to do is when I go down here, I'm going to do something. I'm going to do something really stupid, actually. For size t, I equals 0, I less than, let's see, t dot rows. Oop, my bad. It should be capital T. Then we're going to do plus I. Now we go down here and we do for size t, let's say j equals 0, j is less than t dot calls. Then we do plus j. After this, we're going to go through and we're going to say if t of I, j is less than, and we're going to say 0.12341. Then we're going to say, I'm basically truncating it in a way. I'm saying that, hey, look, this is going to be much easier to read if we see actual zeros instead of 10 times whatever to the negative fifth. We're then going to say t of ij is going to be equal to 0. Over here, let's do g++ and a dot out. Okay, there we go. Look at that. Almost right. Let's change jtot to 3 again. Maybe 5 is better. Let's change it to 5. G++, a dot out. Okay, what do we have here? We have the identity matrix is fine. Oh, the formatting's off. Ah, dagnabbit. 1, 2, 1, 2, 3, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Interesting. Okay, what did I miss? Impleed. I'd say take what he says and apply it to math plus programming logic, not just math. Fair enough. Where if logic algorithm is the correct solution, you do that. If a math solution is the correct solution mixed in with a logic solution, then excellent. So not only math, but algorithms such as well. Because mostly he seems to be examining current algorithms that use math to do the work realistically, he's using that I stated to learn algorithms in math. Yep, that's true. Sometimes math and calculations can take more time than some tricky algorithm. That's what it seems like to me. Am I correct? Okay, so, yes, that's actually totally true. Before every one of these episodes, I know I don't... Okay, I know it seems like I'm actually not preparing for these episodes at all, but actually before each of these episodes, I spent hours going through the literature. For example, for this episode right here, I did a lot of preparation. So let me see. We have quite a few pages of notes in my notebook. I have a paper here just on the, let me see, Lanzau's algorithm and also the power method, which we were planning to use today, but not exactly. So this paper is, I don't know, 20 pages long. I went through some algorithms which I have printed out for Julia code, which is for the DMRG algorithm. I also went through and learned the DMRG algorithm, which is right here. It's about a, let me see. It starts on 10.345, ends on 10.356. So, what is that, 11 pages? Something like that. So, the idea is that I do a lot of stuff before each of these episodes, and it still looks like I'm not doing anything because I'm still learning on the job. The point is, let me see. Also, all the other stuff online. Anyway, the point is, learning the stuff is very, very difficult, right? And it's not because necessarily the algorithm doesn't make sense, because once you get the algorithm, you get a lot of the mathematics beforehand. The problem is learning everything, you know? Because for me, there's always that algorithm I want to learn. For me, it was DMRG. I wanted to learn DMRG. And so I said, okay, I need to learn DMRG. What do I need to know to learn DMRG? Well, that's fine. Diagonalization is something I need to learn. I had only done diagonalization once or twice. I honestly had never implemented a numerical diagonalizer before. So this is the first time I've ever done that. And so, I don't know. My point is, I totally agree with what Edge226 is saying, and that is that it takes a lot of time to learn the math. And if you don't know the math behind the tricky algorithm, then you've got to learn the math before doing the tricky algorithm. Does that make sense? Sorry if I'm kind of all over the place, but it takes some time. So my point is this. If you're trying to learn something new, take a break or take a breather first. Look at what you actually need to know, and then attack everything piece by piece. Say, okay, well, I want to learn something big. And then you need to go through and you need to say, okay, well, is this actually correct? Like, what do I actually need to learn? Do I need to learn this math? And if you do learn that math, just take it piece by piece and go step at a time. That's my best advice, I think. And honestly, it's one of those things that really helps. Like, for example, if you're studying for a class, or if you're in the middle of doing some sort of large research project or a project for industry, and someone puts something on your lap and says, hey, do this, you know, that's really hard just to do this. You've got to split it up into pieces and learn what it is you can actually chew. And that's it. Edge226 complete. Thanks. Sorry for the long talk. But you guys are totally right. That's how it is. Yeah, that's totally right. For software, for everything, really. Okay. So, like every day with Simuleos, we didn't get as far as I had intended to. However, we got decently far. You know, we learned a lot about Krylov subspaces, which, by the way, I knew nothing about for, yeah, please do, Edge226, which I knew nothing about before now. We have done a lot with, you know, diagonalizing something. So what I'm going to do now is I'm going to clean up the code a little bit, and I'm going to commit it to github.com, which is where you'll see all of the stuff that we've been doing so far. Yes, so let me go ahead and do that, and then we'll end by a quick conversation about what's next. So first of all, we can remove all of these guys. I'm actually going to remove all of these comments. Okay, yeah, let's remove all the unnecessary comments. Okay, so we want to still print out the matrix at the end. It's fine to set up the random device twice, whatever, I don't care. Let me see, what else do we need to do? STD vector matrix Krylov, this has been destroyed. I'm going to keep that there. More... do this that is dynamic. Okay. Let me see, what are you doing? Edge226. If you look at the libraries, all functions that do small stuff. If you look at Linux from Scratch book. Oh, I followed that book to create the software. It was like how I do, how do I automate this? How do I, yeah. It's actually pretty cool, doing all this kind of stuff. One thing I want to point out is that Linux has a fundamentally different ecosystem than Windows or Mac. The idea with Linux is that you have a whole bunch of small programs that do one thing well. Not Linux, Unix in general, open source projects are generally this way, where you have a whole bunch of small projects that do whatever it is they're supposed to do very, very well. Which is completely different than, you know, a lot of Windows or Mac applications, where you have one thing that does a whole bunch of things poorly. Think about a whole bunch of apps that you install, and they have a whole bunch of random things that they do for themselves, you know? The idea is that Linux is open and collaborative, and every little small step that you take not only helps you, but it helps everyone else. So you publish those small steps, and you say, hey, look, I've done this right. I don't trust anything else I've done, but I trust this one bit of software. And because you trust that one bit of software, everyone can then use that one bit of software because they trust it, because you did that one thing well. Does that make sense? You always take it one step at a time. You work on something very, very well, and then you kind of add all the things together for a final project in the end. So work entirely in Bash to automate tools. Yeah. I'll take a look at this after stream. Since we're about to end, I think I need to go ahead and clean up the code and commit it to GitHub, and then we'll be good to go from there. Note that there might be a way to do this dynamic. A better way to do this that is dynamic. Maybe I should just... There might be a dynamic way to do this. Okay, what else do I need to do? I'm using Arch Linux. I've been using Arch Linux since I started Linux. I actually really like Arch Linux. It's one of my favorite. The Windows Manager is OpenBox. I created my own special theme for this that uses exactly 3 colors, white, black, and gray. Now, I realize the desktop background has a green color on it. That's fine. But the windows are all very special. Oh, cool. Manjaro. I like Manjaro, but a lot of people don't like it because of the way it uses Pacman and things like that. Now, I like Pacman. It's just the repositories, for some reason, there was something weird about the repositories that I thought people didn't like about Manjaro. I don't remember what it was. Okay, wrote that down. something like this. Let's go down here. I'm gonna leave these guys in but comment it out. We might need them for tomorrow. Okay. Good. Okay, so this is just truncating large, setting values to 0 if they are close. Okay, let me see, what do we have here? Identity matrix from the Krylov subspace. Should be fine. Okay, I think this is fine for now. There are things I do not like about Monjaro and things I do not like about Arch. That's fine. I mean, that's how it is. Orbos, I imagine. What is Orbos? Orbos is the project that you're currently working on. Yeah, the Linux framework. Yep, that's what I thought. Okay, so what I do now is I'm going to run a git status. Okay. Seems fine to me. Modified. Julia, split step, FDTD. Ha. Oops. Seems like I missed a lot of stuff. Yeah, Implete, see you around. Thanks for coming in. Yeah, I will probably be back tomorrow. Maybe, maybe not. I haven't quite decided yet. We'll figure it out. Okay. Lanzos.cpp. That's what we're putting in. Nope. Oh, shoot. Control C. Clear. Okay, so let's do git commit lanzos.cpp message. Adding, let me see. Iterative, how do I put this? Adding iterative diagonalization algorithm. Okay, there's still more to do, but that's okay. Actually, let me do git reset real quick. Let me do git status. Make sure that I didn't screw something up. Should be git diff lan.cpp vi lanzos.cpp. Good. Okay. Run quit. Now let's do git add lanzos.cpp real quick. Now git commit. Oh, okay. Wait. I screwed something up. Yeah, I might take a look. I don't have so much time to watch other streams, but that's okay. Let me just git push. I don't care. I screwed up with git. That's okay. Okay. Oh, it's because I already committed it. Duh. Okay, anyway, that's fine. I went ahead and pushed the changes. It is now available on github.com, which is found directly under my channel. All you have to do is scroll down to the very bottom here, click on my GitHub account, and then go to Simuleos right here. You'll find the latest commit right here. And this is all the changes we made for the day. I think it was pretty good. We got a lot done. And let me see, what else is there left to do? I think that's about it. So, tomorrow or next time we come on, again, tomorrow is Saturday for me, so I may or may not stream, but, and if I do stream, it may not be this material. So it could be, it could be that, on Monday, I come back and I get started on the Lanzo stuff, and it might be that, over the weekend, if I do stream, we work on the Cairo kind of drawing with programming thing again, because I thought that was actually super fun. Okay, what's left? One thing we have to do next is we actually have to implement another diagonalization scheme to take the tridiagonal matrix and turn it into an actual diagonal matrix to use. And again, this is kind of interesting. We might do it tomorrow. This is called like a power diagonalizer or something like that. Anyway, it's in my notes. I will be implementing it next. And that changes, again, our tridiagonal matrix and gives us the eigenvalues and eigenvectors, which are totally useful. And that's about it. So anyway, guys, thank you so much for watching. As always, I really do appreciate it. Edge226, I may show up depending on when you're streaming. And, yep, everything just fell down. 1 second. Oh, I see the problem. Okay, anyway, guys, thank you so much for watching. As always, have a great day, night, afternoon, evening, morning, whatever time it happens to be your time. And I will see you around next time for the next episode of Simuleos, where we do one thing or another. It might be that we work on the drawing stuff, or it could be that we work on the Lanzos algorithm, depending on whether I stream over the weekend or not. Anyway, guys, thanks so much for watching, and I'll see you next time. Bye, guys. Have a great day. See ya.